In this video, I'm going to be breaking down my thesis project, Biosponge Cityscapes. This is one of the main reasons I wasn't really active on socials for a while, and I believe it's worth it. So sit back, relax, and enjoy the show. First of all, the name Biosponge Cityscapes means, so bio means organic, sponge, something that absorbs. Wetlands are organic and they absorb water. So that's why it's Biosponge and Cityscapes because I'm developing on it. So Cityscapes. So that's the name Biosponge Cityscapes. So to introduce the project, this project focuses on two main aspects: development on sensitive areas like wetlands, and how to leverage computational techniques to make the process more effective. This collage mainly shows the significance of wetlands. The image is captured from the site through Google Maps. So here's the proposed site. I chose the nearest wetland to where I was staying at that time. That is Thames Road Wetland near Dartford. It's in London. And this is the site selection strategy where you can see all these hexagonal parts are categorized as SSSI, which means sites of scientific interest. I'm basically not allowed to build on top of it. The rest of this area, the green ones, are okay to build on, but you need special permission. So I have to focus on one of those areas. Also, I've saw this potential of developing commercial areas, residential areas and industrial areas surrounded by this bit. So it's more likely this area would be optimal for the development, and if we leave it a decade or so, this is the area that would be used for further development. This page shows how the open spaces have deteriorated over time. I took the data from Google Earth and then calculated the area to make this graph. This graph shows how the open areas are declining, and this graph shows how the wet areas are declining, or how it peaked and then declines, kind of. So what this shows, basically the land was an agricultural land. So once you break down all the irrigation channels, it became wetlands, and then there was a rapid development after 1999, I reckon, signifying that there is a rapid development that's happening, and also there is a need for intervention. This is a case study that I did near the site that I chose. This is my site. Nearby, there is an urban development in Ebbsfleet Valley. I have noted that through Google Earth data, there is steady decline of wet areas. So I've just studied what they did, and this is how they developed. They just reclaimed the land and they build on council houses, which is basically copy-paste generic buildings, rather than taking advantage of the wetland in general. And this photo is captured when I went to the site. This shows that there is land reclamation that is happening, and if this trend continues, this wet area could be subjected to rapid development and lose its value. I made a collage of stuff I did during the site analysis. I took a picture from the site and I could see the Dartford Bridge, and there were some dirt bike activities going on, and I interviewed these two people and I took some water sample, stuff in general. And this is site access, how you can access the site. One of the main access is Slate Green train station, and this is site context, how the site would look from the outside. So this is the site and all the activities that are nearby. This is basically my urban strategy and how I divided my site based on the physical attributes of the site. This is more like a wet area, and this is like SSSI, and this is more like a site that has room for rural development, and this the riverbed could act as a boundary for wetland. And here's the master plan that I developed from those analysis and everything. I'm just gonna show a summary of what I did in semester A so that you get an idea how I've arrived to this master plan. First thing is the edge of River Cray, where I used this sort of walkway where it acts as a boundary, and these images are conceptual. It's not part of my design, so it looks over the top, but it's not meant to be. I just made it to understand how it could look. I'm going to reintroduce different flora and fauna in the SSSI, and there won't be any sort of development that's going to happen in that area because it is protected. There was pre-existing dirt bike activities, so rather than having it unsupervised, we can make it sort of official, and I've added a lot of sound barriers to protect the other areas. This one's more like the residential area on top of the wetlands, basically eco-living space where the parking spaces are pushed to the edge, and that's actually an abandoned area that is used as a parking space, and the rest not to be disturbed by anything. And there will be like bridges and walkways, there won't be any vehicular access. This is part of the side that I'm going to carry forward for my semester B. So until now, these are master plan strategies, so I haven't got into my design yet. So this is stepping foot into the design part where I'm using some computational strategies to create this master plan first. So the computational strategy that I'm going to use is ABM, or agent-based modeling. So it's based on swarm intelligence. When you see things in nature, like a school of fish, a flock of bird, or beehives, for example, or a termite's nest, you can see that those creatures, if you take it as an individual, they don't have higher intelligence, but if they are in a swarm, they showcase some impressive behaviors. So yeah, this is an experiment conducted in Tokyo. I'm pretty sure a lot of you know about this. They used a 5-sarum, a slime mold. They replicated the Tokyo rail system using tiny food particles. These are basically oat particles. The slime mold found the best possible route, or the most optimal route, to connect this train station in like 24 hours or so. The tool that I'm using is 5-sarum, Grasshopper, which is sort of related to 5-sarum. I'm going to show what I did with it. You can see my site. All these blue spots, these are the entry points that I've assigned. These are emitters, and the major red dots are the amenities. So basically, I've said that in this topography, I want these points as the emitting point, and I want to reach these amenities, these food paths, as quick as, like the most efficient way to walk through this, If the altitude is too high, the agents would take more effort to travel, so that means it would die earlier. I'll show you the animation so you would understand how it works. So you can see how these agents kind of move. If you take one individual agent, what the agent is really good at is predicting its next step, where the agent tries to advance further. Sometimes because of the altitude, it could step back. The agents that step back would eventually die, and the agent that survives would form the pathway. That is the main concept behind it. So it kind of forms the most optimal walkable area. I'm going to skip through the simulation. So these are different iterations. This is the final result, where I allowed the water to stagnate at the lower part of the topography because this place became obsolete. The agents couldn't go through it. Then I added this water body as obstacles. In this iteration, the agents couldn't actually cross this, so I added a bridge and guiding the agents to move through it. There are definitely human intervention, and I'm guiding the agents to do certain things, but mostly the pathways are generative. You can pause and take a look at my different observations here. And so this is the final result that I've achieved. And interestingly, the generative pathway kind of correlates with Christopher Alexander's vision of how a master plan should be, which is a semi-lattice axiom as opposed to a tree structure. So a tree would basically mean there would be like a primary road, tertiary road, and secondary road, etc. But in a semi-lattice axiom system, the path is branched from intersections. And I also created a workflow to find out how walkable this master plan is. I used two different tools to do that. One, 5-sarum, obviously the one that I've used to generate that, and two, Urbano. So I've written a whole dissertation about the workflow that I've created. So what you need to know is how to add certain weightages to these amenities based on Google active times. This will generate a street hit, which is how many times a person would bump into a certain intersection. Based on that, we can generate scores, which is walk score. This graph shows each path score, basically. So you can see this is street hits, and this is street ID, which means the number that correlates with the score. You can see the value and the correlation, how good the walkway is and what's the value of it. So if you have less than 49 as your score, then the area is a bit less walkable. There are a couple dips here, but mostly the area is walkable, and especially it's really walkable near the commercial area. So this is where I'll be focusing on further down the line for my next semester's design. So this is the area that I've chose to develop further. This area is going to be the design, but the area that you can see, the white border, it's the overall building. That's where I'm going to run all the analysis and everything. But this red area is where I'm going to focus a bit deeper and make the floor plans and, all the major design elements. One of my side strategies is, rather than having people walk around the building, why not integrate the pathways within the building, making the space more walkable, if that makes sense. The more the intersections are, the less the travel distance is. That's the graph. Another strategy is, let's push all the parking spaces to the edge, and we'll use delivery hubs for services and not allow proper, trucks and other vehicular access to the building, making it less intrusive. Now here's an interesting part. Just like how we created the ABM model on the topography, we're going to do the same in the 3D space. I'm taking the pockets of the analysis as the building, and it's interconnected by different bridges based on one of my side strategy. You can see where I have all the entry points that I've assigned and the food points making an exit through the bridges. So the intent of creating these entry exit points, so I made sure these agents cover the whole by assigning this entry and exit points. And also there is a void every 30 meters or so to make sure there is enough area for ventilation and everything. So that's basically the preset for the simulation. This is me showing the settings that I've used for running the simulation. So I ran through multiple testings, and I've settled down with a resolution of 10 centimeters by 10 centimeters on X and Y axis. I used a number slider to kind of adjust the Z-axis and check how it works. I started with 4 meters. I've divided that with a number to kind of figure out at what height it will go through while maintaining the levels in a way. So this is the simulation that I've run. You can see the animation. After the simulation, I have the agents spread apart. Now what I have to do is make it into meshes based on proximity. And then I refined the mesh based on different techniques, including shrink wrap and subdivision modifier called remesh in Rhino, for example. I made a 3D printed model to understand the space a little better. And I made an exploded model to understand the vertical axis a little better. I used 3 different strings and kind of replicated a possible pathway of 3 different types of user. So the green user would be a first-time user, more like a tourist trying to explore the space, where they enter from one of the main entry and exit through the bridge. And the blue user is more like a horizontal traveler, more like a window shopper. And the yellow user is more like a vertical traveler, more of a sports enthusiast, more likely explore the space a bit more rather than just sticking with the shopping area. So I use this to determine the ramps and staircases, also to assign different amenities inside the space. Here's the exploded model. And here you can see I have added more stairs and ramps connecting the bridges and making the pathway strongly integrated with the building. And for accessibility, we have lifts, so don't worry about it. It's all sorted. And case studies, some of the main case studies are Eden project. So my project is loosely based on this project. Mainly used the material that they use, ETFE, like a biosphere, and then I added a lot of green spaces inside the buildings. We'll see how it turns out. These are research unit and some case studies that use this material and also use some wooden frames. So my building mostly have wooden frames. I had to take this case study, which is in Paris. And for the commercial space, I'm choosing an Apple store because the values align a little bit, the environmental friendly aspect. So I chose this one. material selection. This is basically the U value calculation and what is the type of wall that I'm going for. So basically using a rock wall insulated wall for partitions and helical pile foundations because I'm adding bridges and it's going to be a lot of foundation. So I'm introducing a foundation technique that is less intrusive to make sure we're not affecting the wetland very much. This is about the ETFE material. And now I'm just going to show how I'm connecting those ETFE through an animation. You can see that in here. So the first set of aluminum frames and the ETFE materials. I'm gonna add some shading areas, selective shading. The process is called fritzing. I'm going to run another analysis to show, the relevant spaces that are suitable for this fritzing, this shading spaces. Here's the second aluminum frame to cover it up, and some holders to hold the bird wires. So here's the bird wire. These wires are a bit wobbly, so I would just discourage the birds hanging around. That's the function of this bird wire. And finally, I'm running this radiation analysis. These are all the geometry data that I've set. This is the geometry that you see here, and these are all the contextual geometries that are around and all the surrounding buildings. This is the solver. You can see the grid size is 1 meter. This is the total radiation that you're getting right now, and this is the analysis period. This is annual radiation. You're getting the radiation from the whole year, basically. So 1st of January to 31st of December. So I'm going to set the fitness factor as minimize the fitness factor. If the number increases, then it will punish the algorithm. I would set the increase in radiation as a negative factor and having more open spaces as positive factor. So these both kind of fight each other. I would try to optimize it for the standard radiation limits while keeping the area relatively open. So this is Gene, and this is solver. I'm going to run the solver. Minimize the radiation, yeah. Start the solver. So this is an 8-hour-long simulation, which I shrunk it down to 10 seconds. The blue hexagons are the open areas, and the brown hexagons are the closed areas. And you can see how it affects the radiation. So this is the total annual radiation throughout the year. That's why the numbers are super high. It's not a big deal because it's just used as a reference value for the optimization. And that's the final result. This is a daylight analysis and the radiation, the initial result. And the final result. The final observation is there are more closed spaces, but we don't have to take it as it is. It's like a guiding factor. We're going to add installations in certain areas. So based on the activities that are there and based on this data that we got, the output is going to completely differ. So this is just a guiding factor, like an initial analysis that we have as a catalyst to determine where to leave it open and where to leave it closed. Yeah, just a deciding factor. Yeah, finally we're into the design part. So this is the area that I'm going to develop further. On a side note, the floor plans are drawn as 2D drawing and everything is hand-drawn in Rhino. And I've used a lot of techniques and automation in Grasshopper to achieve this result. I'm going to show all the floor plans now. So I'm going to explain the floor plans a bit more. This is the roof plan of the building. You can see the shadow effects that I've carefully drawn to show the height of each area. So one of the main thing is the vents, where I had to add like a gradient kind of shadow. If I had to add like 3 different gradients to give the illusion that it's kind of popped up, and you can see how the staircases are connected and everything. You can see the atrium space and how it's connected. Everything is well detailed. It involved a lot of coding in Grasshopper to make it possible, especially these hatches are from Lunchbox, and mainly hatches in AutoCAD in general is like super unreliable. Surprisingly, Rhino's hatches are super stable. Also, you can see these kind of glass hatches. These are stuff that I've done in Grasshopper. This is meant to be 1 to 100 and 80. So you can see like, even the handrails that goes through the staircase is detailed. You can see the difference between the line weight with the stair that goes up and the stair that goes down. So everything is carefully done bit by bit, and it is super hard to appreciate the detail that went into it, so that's one of the reasons I'm creating this video. Yeah, let's go to the next floor. So you can see how the glulam structure is cut off at a place. These dotted lines are for structure grids. To talk about the plan, we have 3 concrete cores. The top floor is more like an outdoor restaurant experience. So we got the main restaurant. It's more like a semi-open food court. Yeah, so there are many areas where you can sit around and more landscapey. And also you have a bird watching spot where you watch birds through these periscope mirrors, which is a way you can enjoy the birds without disturbing it in a way. So yeah, that's about this floor plan. And the next one is level 0. We can see the hidden areas, which is accurately marked, and how the ETFE is going to connect through this wooden mullion. And then it connects to the columns, and everything is thought through. And the next one is, this is a research unit, and it's a lobby for the research unit. And here's the Apple Store, and here's a small retail unit. And there is like digital library space and a normal library space. And here's a coffee shop. And you can also see how the staircases go through as a main way to access the building. And for accessibility, we have these lifts in the core. Yeah, that's the next floor, and you can see how the structural elements revealed itself when we cut through it. And you can see there's a, this is just a circle because you go down a bit more, so it's just a cylinder. And here's the upper part that holds the bridge. Those parts are thought through, even this one. You can see how the land is getting chopped off from here. Because that's like the flood barrier. I've calculated the amount of staircase. You can see how those things are arranged and how this works and everything. So to talk about the planning, so here's a product display area, and here's a seminar hall for the research unit. So you can see a spiral staircase that connects the upper floor and the lower floor for this research unit. And there's a separate entry for research unit, and this is where the public goes. This is where the researchers would access this area. And also we have a tiny recreational space where we can play pool and table tennis maybe. And again, these are library spaces, almost the same as the top floor. And we have retail unit, and the toilet spaces is kind of the same as the top floor. And also, you can see the atrium, and it's more like a bridge here, and you can access the bottom floor, that is the art gallery. So we'll go through that in a bit. So here's the art gallery, and you can see the land is kind of expanded because, you'll see more of land that is chopped. So you can see how that shows up. You can see the dotted lines here. So those columns are aligned properly to the structural grids. This is more like an indoor-outdoor space where you don't have a proper wall. So this is basically an exhibition unit, an exhibition display, and then a glass, and then an exhibition display, and then a glass with a gap. So it's not meant to be a closed space. If the area floods, if the water level increases, this place could be evacuated easily and cleaned up, and then reused and repurposed in different ways. So it's more like an elevated building. Even if there's any flood, or even if the water level increases, this place, the upper parts are pretty safe and functional because of the bridges. And then, this is the only hard space. There's like an office if you want to buy an art or something. So that's not a big deal. And this is a sneak peek of how the place would look. And that's a render, as you can see. And this part is what we developed, and the other parts just as a context. And this long strip is the exploded view. This is, again, the roof plan. I'm showing the section cuts where I'm going to show you the sections that I took. Section AA, section BB, and north elevation and west elevation. Here's another render from the river facing towards the building. This is a load distribution diagram, and this is for construction sequence. You can see this is like a barren land. This is a site that we were given. These are the helical piles for holding the bridges, and the concrete cores and the base, the wooden frame, CLT columns and beams, and then the glulam auto envelope. And then we have the bridges, and then basically the walls and other details. And then finally, we have the ETFE enclosure. Here's some details of the wall and how the system works. Here's the detail about the periscope lens. It is like magnified periscope lens to watch the birds. And I've created a ETFE schedule, of course, using Grasshopper. I calculated the area and assigned a number for it. For example, let's say number 9. Number 9 is here, and this is number 9's surface area. So we can avoid wastage, and we know the exact shape of each ETFE panel. And finally, so for sustainability, we have how the wind flow, ventilation, and also the rainwater harvesting, all those stuff. Visuals, yeah, we'll sit back and relax for a while. So this is the main aerial shot. This is the atrium from top on a rainy day. This is the atrium from level -1. This is the atrium from the library space in level -1. And this is the view of the atrium from the art gallery space. And this is the art gallery, and I'm just showing like what kind of activities are happening here. This is level -1 again. You can see how the staircase connects and also how people interact within the space. Another view of atrium from the connecting bridge. This is the Apple store. And you can see a close-up look of the ETFE panel. And this is a view from the top floor, and you can see pretty much how it looks from the top. So yeah, that's the end of it. Write down your thoughts below in the comments. Also, if you have any ideas for future videos, put it down. I'm working on more tutorials and other stuff, so stay tuned by subscribing to this channel. Also, make sure you leave a like in this video. And yeah, that's it for today. Catch you guys in the next video. See ya.